Hello guys, today we are going to study a little bit about the three Keplers Law. Let's start for the first one. The first Keplers Law says that all the planets in the solar system describe elliptical orbits. Kepler, when was studying all the planets and all these trajectories from Tycho Brahe, he found that not all the data match a perfect circle. So probably there was something that makes that the data from Mars change a little bit. He found that changing the circular orbit for an orbit that is going to be a little bit off the axis, that is one ellipse, all the data perfectly matched. And this information comes from the study from ellipse, and it's not breaking rules. At the end, in one circle, we are going to have everything at the same distance. But if I keep, for example, here everything at the same distance, you're going to see that the ball is going to be falling. But if I start to move and make little change, you are going to see that the center of gravity is going to allow to this to keep moving around. So that's probably one way to explain. In the case for the ellipse, we are not going to have a perfect center of gravity. In that case, we are going to have a perfect circle. But in one ellipse, the sun is going to be a little bit off the center. Something that the Greeks call focus, that means fire. It has sense to have the sun in the region for fire from the ellipse. And sometimes the planet is going to be very close to the sun, sometimes we are going to be very far. So keep in mind, all the planets in the solar system with close orbit describe elliptical orbit. That is more simple than a circular orbit. We can define that a circular orbit is an elliptical orbit, but with the foci, both focus, are perfectly in one point. So it's one example. Second Kepler law, all the planets with orbit describe equal areas in equal periods of time. What does it mean? It took a lot of time for Kepler to understand that, and I make one drawing describing in this elliptical orbit. Sometimes, believe or not, when the air is closest to the sun, that happens around December 21st, 22nd, we are going to be closest to the sun. The north hemisphere is very cold because it's different. The axis of the air is pointing away from the north hemisphere, but the south hemisphere is going to be really, really hot. It's going to be summer. Okay, so in December that we are very close to the sun, suppose that we describe in 31 days, from December to January, this part. 6 months later, whenever we are June and July, we are going to describe in 31 days exactly the same, but you can see that the planet is moving very little. So if we go to create one area, that go all the area from the point of the planet to the force of gravity, that is the sun, is going to be exactly the same area that was described. For this reason, it's called equal areas in equal periods of time. But to show you with this little example, let's see if this has sense. I mentioned when the planet is really far away, you see, it's moving very slow. But what happens when it's close? It's moving really fast. Okay, I'm going to return one more time. Very far, it's moving very slow. But when it's very close, it's going to be moving very fast. So, again, when we are very close, the planet moves really fast because we have a big pull, exactly the pull that I have created for my hand here. I decrease the pull, I move fast, slower. Increase the pull. So when we are very close, or one planet is very close, it moves really, really fast. But when it's really far, it moves very slow. But it keeps the same proportion for the gravity. It's going to be the same string, the same force created from the sun. That's described the second Kepler law equal areas in equal periods of time, or we can say closer to the sun, faster than the planet is going to move. Far from the sun, it's going to be very slow, but they keep the same proportion, the same force. Third Kepler's law. Probably this is the most mathematical law that Kepler found. It's after make a complicated graphics that he found one relation between the period. The period is to describe the time that it takes to this one planet to revolve around the sun, to complete one orbit. In the case for the Earth, 1 year. Okay, and semi-major axis. What is the meaning of semi-major axis? Let me explain here one ellipse. We are going to have different points. Let's go to this with C, the central point. Okay? If we start to move around farther away to deformate the ellipse, we can call the focus. In plural, because we have two, we call foci. Okay, the sun is going to be in one of these foci. Now, the point, maximal point from one vertex, one side crossing the center, both foci to the next vertex, the next point farther away from the center, we call to this line or this distance the major axis. If we go 90 degrees crossing from this vertex, crossing only the center, perpendicular to the major axis, we are going to have the minor axis. But the distance that we have from the center to one of these vertex, the maximal vertex, is what we call the semi-major axis. Semi means half. And it has sense. If you see, this is the major axis divided by 2, and we are going to have the semi or half major axis. That we use the letter A to denotate semi-major axis. So don't surprise that usually you are going to find period square, P square, equal A cubic, that represent the semi-major axis. Remember, for that A, have the axis. In fact, all the data that you have in the books, because every day the distance from one planet is changing with respect to the orbit, we usually give you the average distance. So the average distance is taken from the center of the orbit to one of these maximal vertex. That is semi-major axis. Now, this way, Kepler found that you have period square is going to be exactly equal to the cubic of the distance that exists between the center of that orbit to the vertex for every single planet. He never understood that we have different units. Period is units of time, and semi-major axis are units of distance, cubic. Many years later, Newton adds one constant that keeps the constant. And what is constant for all the planets in the solar system? The sun. He was adding the gravity created from the sun to improve this formula. Okay, I hope this helped you today. Thank you very much.